Good afternoon, everyone, and welcome to the Great Lakes Seminar Series, co-hosted by the Cooperative Institute for Great Lakes Research and the NOAA Great Lakes Environmental Research Laboratory. My name is Mary Ogdahl, and I'm the Program Manager for SGLR. It's my sincere pleasure to introduce today's speaker, Dr. Silvia Newell. Dr. Newell is an Associate Professor of Aquatic Biogeochemistry at Wright State University in Dayton, Ohio. Her research focuses on nitrogen cycling in eutrophic systems around the globe, from the Great Lakes to Lake Okeechobee to Taihu, China. She was the co-chair of the HABs Collaborative from 2018 to 2020 and currently serves as the president of the Lake Erie Area Research Network. She is currently NSF funded on projects in Lake Superior, Lake Erie, and the Maumee River. She is also part of the monitoring team assessing the H2O Ohio wetlands. Before I turn it over to our speaker, I would like to remind everyone to please leave their microphones muted for the duration of the webinar. You are welcome to enter questions into the chat box at any time during the presentation, which I will moderate at the end of the presentation. With that, I will turn it over to Dr. Silvia Newell. Welcome, Silvia.
Hi, everybody. I wish I were giving this in person as the last time I gave a SGLR lecture, but this way, hopefully more people can attend. So yeah, I guess that's our trade-off now with COVID, right, is accessibility for being in person. So anyway, today I'm going to talk to you about nitrogen availability, both as a driver of harmful algal blooms, but also whether it might be the piece we've been missing in terms of being able to model microcystins and possibly toxins in general. So as we know, everyone in this webinar knows, I'm sure, Lake Erie has had a cyanobacterial harmful algal bloom problem for a long time. But back in the 60s and 70s, our main culprits were Dolichospermum, Manabena, and Ammonium. And now we have Microcystis. And why does that matter? What's the difference? We're trading out one cyano for another. Well, nitrogen bioavailability probably plays a really large role in who's there. So both Dolichospermum and Ammonium are able to fix nitrogen. And nitrogen is really hard to fix. The gas is triple bonded. It requires 16 to 18 ATP for each nitrogen gas molecule. So it's really limited in terms of bioavailability. And something like Microcystis can't fix nitrogen, but it's really good at using these useful forms of nitrogen like ammonium, urea, phosphate nitrate. And it turns out that nitrogen is really important for toxins. So microcystin particularly has 10 nitrogens per molecule of microcystin. So that's a lot of nitrogen for a single molecule, right? And when cyanos go to take up that nitrogen and eventually turn it into toxin, it's really, really easy to take up ammonium. It's a little harder to take up nitrate because it has to be reduced to ammonium. Nitrate has to be reduced to nitrite and then ammonium. And N2 has to be reduced all the way to ammonia, and that takes a lot of energy. So basically, the kind of nitrogen that we use or that we make available in the water might matter a lot for who is able to grow and proliferate there. And we know that these chemically reduced, as in ammonium, urea, they've got hydrogens on them instead of oxygens. When you add those, it can really help non-nitrogen fixing cyanobacteria both grow because they're super competitive for it, but can also increase their toxicity. And there's a nice paper over here from Justin Chaffin showing that basically no matter what kind of nitrogen you add, you increase microcystin concentrations versus a control or a P-only treatment. And there have been other papers showing that not having enough ammonium around can inhibit toxin production, and that the Matt Harkey's paper with ammonium urea uptake both leading to microcystis biomass and toxin production increase. And so when we think about managing nitrogen and phosphorus and looking at nutrient loads and trying to think about the impacts of that on the size of blooms and the toxicity of blooms, I really like this figure from the Chris Gobler et al. Harmful algae paper and issue, showing that if we think about just reducing nitrogen, we might end up with smaller blooms but that are super toxic, but they're nitrogen fixers, so they might still be kind of large blooms, depends. But we know that if we reduce phosphate, the blooms are definitely going to be smaller, but they could end up being super toxic. And that seems to me like generally a pretty bad idea. So this is where I make my plug for when we're talking about managers and people who are dealing with and worried about toxic, harmful algal blooms. We should really be worrying about reducing both nitrogen and phosphorus to try to not support those blooms. And so then going back to nitrogen form, like I said, nitrogen form matters for cyanos. They are really, really good at using ammonium, urea. Notice that urea here is basically 2 ammoniums with a carbon on it, so you cleave this off and you basically get double the ammonium. But nitrogen gas is really hard to use, and nitrate is also kind of expensive to use too because it has to get reduced. And it turns out that we've been shifting the kind of nitrogen that we add to surface waters around the world, not just in the US. We used to be adding mostly urea ammonium nitrate prior to the mid 1990s, and possibly in the US at least due to the Oklahoma City bombing, but it does seem to be a bigger global trend, so I'm not sure exactly why everyone decided to do it. But if you look at a 2011 use of nitrogen as fertilizer around the world, you see that in the US alone, about half of what we add of synthetic fertilizer is either urea or ammonia, and then the other quarter is urea ammonium nitrate. So urea, ammonia, they're huge amounts of what we add as fertilizer, and so that chemically reduced nitrogen is like the main thing that we've started adding to the world now. Now, obviously, that can get nitrified within soil and you still end up with nitrate runoff, but there is a lot of reduced nitrogen directly being added. And while diatoms use and store nitrate really efficiently and they're quite good at it, cyanos greatly prefer and are really, really good at taking up urea and ammonia. It's not that they can't use nitrate, they do. It's just that they use urea and ammonia first based on their nitrogen control ladder. So today, the majority of my work then is going to focus on nitrogen cycling in Lake Erie. And a lot of what I'm going to talk about is a study that was headed by a PhD student, Daniel Hoffman, who is now a postdoc at Kennesaw State University, and he was co-advised by Mark McCarthy and myself. And here's where I have to give a big shout out to Noah Glirrell, because going out on the Noah Glirrell boat was the main reason Daniel was able to collect samples and do his entire PhD project. So I want to thank you guys. And also on this paper, which is now in review at L&O, are Tim Davis, Ashton Bodecker, Justin Myers. So Daniel's study focused then exactly on the western basin of Lake Erie, which we all know experiences harmful algal blooms. We know that the Maumee River watershed is 88% ag use, so there's a lot of fertilizer and manure that gets added, and we know that in terms of the general study of Lake Erie and nutrients in the last 20 years, there's been a lot of focus on phosphorus because of the tight correlation between SRP load and biomass. But we also know that nitrogen's been considered more recently, and it's not that it was ever, I would say, not considered at all, but given the lack of strong correlation between, say, nitrate and biomass, it sort of got a little bit ignored. However, we now know that the ratio of non and nitrate nitrogen, so killed all nitrogen or total killed all nitrogen, to nitrate in the watershed has been increasing over the last several decades. And here you can see a figure from a paper I headed in 2019 showing that that ratio has changed greatly by a decade in terms of what's coming out of the Maumee Weekly. That's mostly due to decreasing nitrate, but still the ratio itself has changed. And we know that in Lake Erie, the cyanobacterial community has shifted, like I said, from nitrogen fixers to non-nitrogen fixers. And there's also a preponderance of evidence now that shows that nitrogen stimulates increases in biomass, upregulation of toxin-producing genes, etc. And so why then, when we try to look for relationships between nitrate and biomass, ammonium, and particulate microcystin, or the ratio of ammonium to nitrate to particulate microcystin, we don't really see a good relationship. In fact, what we end up seeing a lot of times is this more hockey stick thing over here that seems like there's some, threshold above which you end up seeing higher levels of microcystins, or below which you end up seeing higher ratios of ammonium to nitrate. And I think that that is really because snapshot concentrations of ammonium is not a good way to represent nitrogen availability. In fact, it's sort of the opposite way to expect nitrogen availability, right? We know the first thing cyanos are going to use is ammonium. And when they start proliferating in biomass, they start drawing down the ammonium, and then they draw down the nitrate. And as they're drawing those concentrations down, the toxin in biomass goes up. And it makes sense, right? You take up nitrogen, and when you've got nitrogen around and enough of it taken up in enough biomass, you start seeing, high concentrations of particulate microcystin, but the concentrations are low. And so there's like a time lag and a trade-off here. So it's not that high concentrations immediately equal high biomass. The concentrations get drawn down, and then we see more particulate microcystin. So I don't think that snapshot concentrations are the best way to look at that. And so what Daniel did was he focused on this exchange of ammonium between organic matter, so cells, right? The cells, they take up ammonium, and then those cells, they can lyse, they can sloppy zooplankton feeding, fish poop, viral lysis, be broken back open or recycled in the fecal pellet express. And you've got remineralization, regeneration, ammonification, whatever you want to call it, is re-release of ammonium. And that this arrow here of re-release of ammonium, that's really what represents the ammonium availability, not the concentration at any given moment in time. And so if you think about uptake, then we're talking about uptake by everything in the system, everything from cyanobacteria to nitrifiers to any single-celled organism, really. And that's, we think of that as a community demand, is if you give them ammonium, how much can they take up? And then there's an internal resupply. So as all of these cells get broken down or lysed or remineralized and recycled, that's the ammonium that's actually available. When the concentration is low, it's the recycling that dictates the ammonium supply, not any given concentration at any moment in time. And we're going to call that regeneration here for the sake of internal consistency with the literature, but there are a million words for it in the literature. All right, so Daniel went out with Noah Glirrell monthly for 2015, 2016, and 2017 as part of his PhD research. And he took a lot of the pictures here in addition to this being his data. And we relied on the Noah Glirrell monitoring for a lot of things, but Daniel took samples for his own nutrients, and he also did the stable isotope incubations. And it's a little bit complicated, but the idea is that you add a relatively high level of 15 ammonium. In this case, he added 8 micromolar. And you add it to triplicate bottles that you incubate in the light and triplicate bottles that you incubate in the dark. And then you leave those for 24 hours. And after 24 hours, we assume that cells take up both 15 and 14. And so we do know how much 15 we added, right? And so the 15 that is gone, we assume is in proportion to the nitrogen that is taken up as a whole. And then any new 14 nitrate that's made, we assume that's the regeneration. That is the new 14 that's made. So these are equations were independently developed by both Blackburn and Capron in the late 70s, and we still use those today, and they seem to work pretty well. So this is showing the stations that Daniel focused on. I think in 2015, he did mostly WE6, WE2, and WE4, and then we ended up adding WE13 in 2016 and 2017. And WE6 obviously is the most influenced by the Maumee Bay. WE4 is most influenced by the Detroit River, and WE13 is definitely the farthest away from both sources. So these graphs are all going to be displayed in relatively similar order, right? So we have the stations here at the bottom. So we've got WE6 coming from Maumee Bay, then WE2, WE4 is that one from Detroit River, and WE13 is the farthest away one. And that's shown here for both the uptake and regeneration numbers. And his treatments here are shown as light green is the light treatment that was incubated in the light, and dark was what was incubated in the dark. For regeneration, those light and dark incubations were not different from one another, so they've all been shown together here. And what you can see for the uptake is that these are all of his sampling dates over all of the years, and that the light incubations obviously have higher rates of uptake than the dark, because we know phytoplankton are more active when they have light immediately available to them for energy. And so there is a significant difference between the light and dark treatments for how fast ammonium is taken up. You can also see that there's a general decline in how fast things are taken up as you move away from the river mouth, which is pretty expected as you're going down in both nutrients and biomass as you move away from the river mouth. And regeneration shows a very similar trend, although W6 and W2 are not significantly different from one another. But what I'd like you to notice here is that the amount of regeneration that's actually available is up to about 0.2 micromole per liter per hour. And for all of you who have measured ammonium and go, but I can't even measure it, it's below detection limit. Well, that's because it gets taken up even faster at 0.2 to 0.5 micromole per liter per hour, but there is a lot available there. It's just that it gets used also very quickly. And so if we look at this a little differently now, if we look at all the stations together by month instead of with distance from the various river mouths, you can see that for uptake, we get really, really high rates in July and August and September, as one might expect during the bloom. It's pretty variable in June and starts decreasing again in October. It's pretty low in May before you get a lot of biomass. So this makes a lot of sense. This generally follows the biomass trend that we expect to see. Regeneration, on the other hand, really peaks in June and July and then goes down after that. And so June, July, and August are significantly higher than September or October. But again, the range here is pretty high, and you can have a relatively fast resupply rate here. And so if we look then at how much of that community demand is actually supported by what's being turned over, see that there's enough activity that by May, 50 to 75% of the demand's already being met. In June, it's up to 100%, and then it sort of decreases as you go further along in the bloom. But what's really interesting here is that it can still supply, 25 to 75% of the demand. This internal resupply can support that much of the demand even in peak bloom season. And when you look at what is coming in from the Maumee River, so this is showing metric tons of total nitrogen coming in from the Maumee River in the week before Daniel took his samples. And you can see here that although in May and June, and even occasionally in July, there's still quite a bit of TN coming in from the river. By the time you get to August, September, there's almost nothing. And so where's the nitrogen coming from, right? Because you only have like a 60-day window in the Western Basin max. So it really must depend a lot on this resupply of nitrogen at this time, this ammonium turnover, to be able to support and maintain these harmful algal blooms. So Daniel did these calculations and showed that in the Maumee River, there's between 27,000 and 39,000 metric tons of TN per year coming in. And when you scale up his regeneration rates, you see that that internal resupply of ammonium can actually account for 60 to 75% of the annual load of nitrogen into the Western Basin. And that's pretty impressive that with such a short residence time rate, it can still supply this large amount of nitrogen. And I think that that's really critical for sustaining and maintaining these harmful algal blooms. Now, just to divert sideways for a minute to talk about another project. So this was a different PhD student, Dr. Justina Hampel, who's now a postdoc in Sweden at the University of Life Sciences. And she was also co-advised by Mark McCarthy, and we did this particular project in collaboration with George Bullerjohn, Mike McKay, and Michelle Nudek. And she went out and looked at Sandusky Bay, which I guess is debatably western basin of Lake Erie, and did a similar thing where she also looked at ammonium turnover rates for the Planktothrix bloom that was that year, definitely in Sandusky Bay. And what she figured out was if she scaled up and compared her ammonium regeneration, or that sort of internal supply rate, versus what was coming in from the Sandusky River, she looked at the sampling date that she went. So she went 4 times here in June, July, and twice in August. And she looked at how much TN was coming in that particular day, and then she looks at the range, the weekly range here of metric tons. So you can see that that actually is pretty extremely different even within a week in June here. And then if you look at just how much of that is TKN, or again, the more bioavailable form of nitrogen, it's less, but there's still, a significant amount. And then if you compare that to how much regenerated nitrogen was coming from her rates, it's really, really different. So you can see that in June, maybe the regenerated nitrogen is super high, but it's only like 2 to 5 times as high as what's coming in from the river. By the end of July, that's 25 to 50 times higher. By mid-August, it's 380 to 500 plus times higher. And by the end of August, when everything is in, super bloom competitive dying off sclerotic mode, the amount of regenerated nitrogen accounts for more than 1,000 times what's actually coming in, because there's so little water actually coming in through the Sandusky River at that point. So I think that this is a more extreme version of the Western Basin, right? Because it's a smaller river and it's more enclosed, but I think it nicely illustrates that importance of internal resupply of nitrogen to maintaining a harmful algal bloom. Okay, so if we go back to Daniel now, as you know, a lot of times when we try to measure or model microcystins, there's not really one good parameter or a couple good parameters that have a strong individual correlation with microcystin, or it caps out at like 0.4, maybe 0.5 R squared. It's really hard to predict exact concentrations or when they're going to be low particularly. And so thanks to the GLERL weekly monitoring, we have a lot of these data that we're able to use. And so Daniel was able to have both particulate and dissolved microcystin concentrations, and that really nice large data set, plus his own data set of ambient nutrients that we'd collected, as well as the uptake and regeneration rates for ammonium. And if you plug all of this potentially into a model and you're trying to fit the best subsets regression approach, or we also played around with an AIC and trying to figure out which combination of parameters are least correlated with each other but best together represent the concentrations that are available. You can see that we get a pretty good correlation here. So on the x-axis is showing the predicted value, and on the y-axis is the actual value. And there's a really strong correlation here, and so we get an R squared of 0.831. And I'd say that's pretty darn good, particularly in the world of microcystin. And again, this is all in review at LNO now, so we'll see what happens. So what went into that model? Well, in this case, there are a lot of things that go in there, and I think it's important to acknowledge here that phycocyanin biomass takes up, accounts for half of the explanatory value of the model. And then about a third of it is accounted for by things like temperature and nitrogen concentrations. And so nitrogen concentrations together, different forms of nitrogen, account for about 12% of the variability that we can explain. But nitrogen turnover, so this includes both uptake in the light as well as uptake in the dark. So remember, those are the bottles that are incubated separately. So we think that the dark incubation is more representative heterotrophic uptake. Not that phytoplankton can't take up things during the dark, but obviously they're doing so more actively in the light. and then regeneration accounts for about 8% of it. So together, that's about a third of the explanatory power of the model. And that's pretty important. So when you're saying, okay, well, I can only get an R squared of 0.4 or 0.5, well, if your total R squared is 0.83, that makes sense, right? If your uptake and regeneration could be explaining about a third of it. So this is well and good and exciting. I was really excited about it anyway. But there aren't very many people in the world who are going to measure uptake and regeneration, although if anyone wants to start doing it, let me know. I'm happy to share the wealth. And so one thing that we tried to do was say, okay, well, if you can't measure uptake and regeneration, if you don't have the power to use oxmims or measure 15-ammonium, what could you do? And so what Daniel tried to do is he tried to put together models for modeling uptake and regeneration separately based on things like, well, unfortunately for uptake, about half of it is regeneration. So, but the NP load of the Maumee River, air temperature, ammonium concentration, nitrate concentration, urea, even Secchi depth, and turbidity as measures of basically cells, I assume. And regeneration is about half of that. And that has a pretty good R squared, again, of 0.82. The regeneration is harder to model, but a combination of, again, biomass, chlorophyll, PAR, conductivity, dissolved inorganic nitrogen, nitrate, how far along in the bloom we are, accounting for, July 1st or so is basically day one. And air temperature and TN load, you can get kind of there. So an R squared of 0.689 is not terribly bad. And so the idea is possibly if we get better at modeling these uptake and regeneration, you might be able to then use a nested model to predict uptake and regeneration, and then use those things to predict microcystin, because these are all things that we know pretty well what they're going to be, right? By, June or so, when we know what the rain's going to be, we get an idea of what the load's going to be. It gives us a pretty decent idea of the size of the bloom with P, and then you could, in theory, predict how toxic it's going to be or not. Obviously, we're a few stages off from that, but I think it would be really exciting if we're able to do it. And so then another question is, well, how well does this work outside of Lake Erie? And I think the answer is that every lake is going to have a slightly different combination of parameters that work best in that particular lake. But I think that Grand Lake St. Mary's is an interesting case study. And there's a grant that Mark McCarthy and Stephen Jackman and I got funded a couple years ago, and a grad student named Joe Davidson has taken the lead on that. He's looking at nitrogen cycling in Grand Lake St. Mary's. And as part of that, one of the things he did was measure uptake and regeneration in the water column for 2020 and 2021. And if anyone has been paying attention to what a weird water year we've had this year, you know that we basically didn't really get any spring rain, right? We got late summer rain, we got fall rain, but we didn't get a lot of spring rain. And so the way that that translated into Grand Lake this year was just weird. There wasn't much of a bloom for the first time in a decade in early spring, and then instead of just being straight up Planktothrix, it was Planktothrix, Aphanes, and Microcystis, and they all duked it out for a couple months, with a week here and a week there, smelling like grass or looking blue. The Microcystis turned blue. They were very cranky. It was weird. And now we're back to the, straight up Planktothrix bloom, so no one worry, Grand Lake's still doing its thing. But that means then that we had really different biomass and microcystin values between 2020 and 21, and you can see on this graph here of the model that we've got high microcystin and low microcystin, and this is basically 2020 versus 2021. But what's nice about that is for once we actually spanned a pretty good range of microcystin concentrations, and so for the Joe's uptake and regeneration values are super preliminary, and they're definitely not final yet, but for fun, I plugged them all into a model to see if we could use them and the other parameters that are collected at the lake to try to figure out microcystin concentration. And it turns out you can get a great R squared. This one is 0.96 basically, it models it super well if you take into consideration not only biomass shown here as chlorophyll, also total suspended solids, which is a thing that Stephen Jackman measures. But if you need, you also need uptake and regeneration, and those together, again, account for about 1/3 of the variability of the model. So that seems pretty consistent. It's something along the lines of biomass. You need at least half, you need that to explain at least half the variability. But then I think you need something more, and to me that more is the nitrogen availability. And nitrogen availability is really shown best by ammonium uptake and regeneration. So it's not just snapshot concentrations, because those don't reflect well what's inside cells, right? What's available to cells is best shown by this turnover. And if we include that turnover, we see a lot of explanatory power, I think, for microcystins. Again, this one's super preliminary. Joe's working on his thesis now, so we'll see how that goes. All right, so in summary then, we can see that ammonium regeneration helps sustain non-nitrogen fixing blooms in Lake Erie that accounts for 20 to 60% of the demand, even at peak biomass. And this is really important because that peak biomass time correlates to when water column nitrogen concentrations and external loads are extremely low. Additionally, we think that ammonium turnover rates, not concentrations, might be what's necessary to accurately model toxin concentrations to get us past that R² of about 0.5 or so. And so our take home then is that we're suggesting that development of bloom models and/or a nitrogen budget for Western Lake Erie must account for internal resupply processes such as ammonium turnover. All right, so I'd like to thank current and past members of the lab, Wright State, and particularly Ohio Sea Grant for funding Daniel's basically entire PhD and the vast majority of his work, in addition to the Great Lakes Environmental Research Lab and Sigler for, Daniel to be able to go out on the water with you guys. It was really great. So we really appreciate it. And at this point, I will take questions.
Thank you so much, Silvia, for that wonderful and very interesting presentation. I expect that we'll have some questions and discussion. I don't see any questions yet in the chat, though, so I'm going to invite people to raise their hands, and then I will unmute you so you can ask your question yourself. And of course, if you're more comfortable typing it in to the chat, you can do that as well. Okay. Now it's my job to make sure I can find all the raised hands. Okay, so I see a question from Sandra. Sandra, I'm going to allow you to unmute yourself. Okay, Sandra, I'm not sure quite how to say your last name, but Sandra Bin, you're able to unmute if you have a question for Silvia.
Okay, I'm sorry. I had technical trouble. So thanks for allowing me. And I'm not the researcher like so many on this webinar are, but I'm wondering in terms of the source of the urea and whatever, have you looked at how much is coming? Because we know they've changed the composition of commercial fertilizer applications that does have it in it, and manure. Are you able to distinguish between those in terms of what the inputs are that are, playing this role?
There are people who are stable isotope nitrogen experts who could theoretically do that, but because I add 15 nitrogen as a tracer, that basically eliminates me from the bunch of people who could safely do that in their lab. So yeah, I assume a lot of it is coming from manure as well, but I can't determine that from my work.
Thank you.
Okay, thanks for that question, Sandra. Next question from Catherine Hyde. Catherine, I'm going to allow you to unmute yourself.
Hi, thanks so much for such an interesting presentation. I was also just thinking about your work in terms of trying to develop nutrient criteria, nitrogen criteria in particular, for lakes with the goal of minimizing the threat of, microcystin and harmful algal blooms. And, I just really take to heart your point about, these standalone ammonia measurements maybe not being the most useful. But of course, that's how we normally evaluate water quality. I don't know if you have any thoughts.
Well, so in exciting news, oh gosh, there are like 8 PIs, but Becca Munich, Christine Kirchhoff, Mark McCarthy, Hans Perl, it's going to be Chris Ward at Bowling Green, and like 4 more social scientists, including Robin Wilson at Ohio State. And I just got this giant NSF DICES grant funded, and we're trying to look at how much do we need to reduce nitrogen coming out of the Maumee River to set a target for Lake Erie to try to reduce both toxicity and size of harmful algal blooms. And then what does that translate to in terms of in-river nitrogen processes that are included in the SWAT model that Becca's been using to try to make the model better, and then trying to work with farmers to figure out what management practices farmers are actually willing to use and adapt, and trying to weight the SWAT model for what things are actually likely to get used. And then hopefully we'd be able to make recommendations not only about how much nitrogen needs to be reduced, but also what's the best way to do that people may actually do. So I'm super excited about that project. I'm really glad it's gotten funded finally, and hopefully we'll be able to make some better and more exciting recommendations about that somewhere down the line pretty soon.
Nice, thanks.
And next, Hank Vanderploeg, you can unmute.
Yes, thank you. Silvia, what do you think are the main drivers of regeneration?
Well, again, regeneration is a word that we use interchangeably with remineralization, ammonification, mineralization, right? People call it everything. It's basically just respiration of organic matter that also releases nitrogen. And so anything that's a driver of respiration is going to be a driver of nitrogen release, because it's also a driver of carbon and phosphorus release. So as you have more biomass, as it's warmer, as you have a proliferation of heterotrophic bacteria, which we know that we do in Lake Erie, all of those things are going to increase rates of respiration. But biomass and temperature and ultimately nutrient loading driving that biomass are the main things.
Just to follow up, is grazing a factor in regeneration?
Sure, right. Sloppy feeding by zooplankton is definitely a thing that releases or can release nitrogen. Also, zooplankton poop, fish poop, all those things re-release organic matter that heterotrophs can break down and remineralize.
Okay. Thank you.
Thank you, Hank. All right, we do have a question in the chat that I'll read from Rusty Gowland. The question is, what type of nitrogen and how much of it comes from air pollution?
So you can have NOx, and so NOx falls out of the sky pretty easily. We did some rain measurements here. Mark McCarthy did with an undergrad student, Tommy. And we found maybe like 5 micromolar NOx in wet deposition. And I think in dry deposition, we did a back of the envelope calculation once, and I think it was across the entire Lake Erie, not just the Western Basin, maybe 5% of it was coming from atmospheric deposition. And so it's not that it's not important, I think it is, but it's relatively small by comparison.
Okay, thanks, Sylvia. And Rusty, if you have any follow-ups to that, feel free to raise your hand or type in the chat again. The next question in the chat, I apologize in advance for not pronouncing this correctly, but it's from Ayulawatio Coker. And they asked, they just want to clarify, so the N14 was used to measure nitrogen uptake, while the N15 was used to measure nitrogen regeneration for the incubation experiments. Is that correct?
That's not correct. They're both used for both. We assume that as the 15 nitrogen goes down over 24 hours, that's representative of all nitrogen being taken up, right? And so it's in proportion to how much is how much of the pool each thing is. So, you know, you might have, if you had fully half 15N, right? And half of your 15N was gone, we would assume that twice that much got taken up total of all nitrogen. And then we account for that as the 14 nitrogen that goes down. And then if you've got a change in what you would expect your total 14 nitrogen concentration to be after 24 hours with that uptake, if you've got more nitrogen than that around, that means there must have been additional regeneration as well. So those Blackburn and Capron equations account for both. But you're only making new 14 nitrogen, you're not making any new 15 nitrogen, we assume.
Okay, thanks for clarifying that, Sylvia. Next, we have Mark Rowe with a question. Mark, I've allowed you to unmute yourself.
Hi, Sylvia. Thanks
Hi,
for
Mark.
that really interesting presentation. I guess your studies kind of focused on the pelagic system. I was wondering the importance of the benthic processes like coupled nitrification, denitrification at the sediment surface, or regeneration of nitrogen by dry-scented mussels or something like that. Do you think those could be important for the nitrogen supply?
Yeah, so that's a great question. And the reason, so Ashlyn Bodecker is an author on this talk, but she also published a paper in 2020 where over 2 years she looked at coupled nitrification, denitrification, as well as flux of all nitrogen species across the sediment water interface in the western basin of Lake Erie. This was a grant that Mark McCarthy got funded through Ohio Sea Grant. And we did look at net ammonia release from that. And Daniel has a comparison of that compared to internal water column resupply. And I think that the sediment ended up being about 10% of that, although I'd have to, if Daniel's here and he wants to clarify that number, please do so. And so it is important. We did look at that. I will say that Ashlyn did have some samples that probably had some mussel, they had mussel shells in them, but we haven't looked at mussels directly yet. And that is a thing that I still would really like to do. I tried to talk Hank into it once, it didn't go anywhere. But if anyone wants to do that, please let me know, because I'm super interested to know broadly how much do mussels contribute to that ammonium resupply.
And Daniel, would you like to chime in? I saw you raised your hand. You can unmute if you'd like to.
Yeah, I'll just confirm what Sylvia said there. It was about 11% when we compared Ashland's sediment release data for ammonium to our regeneration rates. And I'll also just kind of chime in briefly on the dry-scented mussels as well. While we haven't measured that directly, I did do kind of a thought experiment during my PhD where I took literature values of ammonium release rates and compared it to the incoming TKN load of nitrogen from the Maumee River, and kind of assuming a half year, it was like 21,000 metric tons of nitrogen release from dry-scented mussels as ammonium. So it could be a huge contributor, but certainly not something we were measuring in the bottle incubations.
Okay, thanks for that, Daniel. Okay, now back to the chat. Alan Burton typed in, great presentation. Sorry if I missed this, but sediments in the Western Basin have huge concentrations of N and P. What role did they play?
Yeah, so I think we've just addressed that, and Daniel did say it's about 11% of the releases to compared to his water column. If you scale it up, to 3D to the Western Basin, it's about 11% of the water column, or the total with the water column.
Okay, thank you. Next question in the chat from, Alan says thanks. Next question in the chat from Irma Liebhardt. Can you tell the difference between nitrogen from fertilizer versus nitrogen from manure? And if so, the amounts or percentages of each?
Right, so again, this is a thing that can theoretically be done with nitrogen natural abundance stable isotope signatures. And I hope that someone does look at that more eventually, but given that I add stable isotope tracer to everything. Basically my whole lab is contaminated with 15 nitrogen, so I'm really not the best candidate to do that.
Okay, thank you. And there's a question here, and okay, let me go on to, so Mark McCarthy entered a citation in the chat here saying that they looked at Joyceans in sediment nitrogen cycling in Saginaw Bay, so there is some history on that. And so people are interested in looking at that. He put the citation in the chat. Okay, so I don't see anything else new coming, so people please enter questions or raise your hand if you have anything else to ask Silvia. Okay, Rusty, I'm allowing you to unmute.
Okay, thank you. Thank you, Silvia, for so much information. I'm getting a lot of insight. The lake of my concern, I lead a lake association in northern Michigan. And what's surprising to me is our lake is very pristine. We have low levels of both nitrogen and phosphorus, but we have highly concentrated blooms with high levels of toxicity in the fall. And we do have zebra mussels, which we've talked about, but I'm looking for what are the controllable and non-controllable sources of the toxicity. And I think you've answered the two that I don't think we have any control over are the regeneration from zebra mussels, air pollution, and it seems like since we don't have heavy sources of nutrients, like we don't in our tributaries have real high concentrations except in the spring, which is biomass.
Does your lake have a strong hypoxic zone? Like, does it go anoxic in the bottom in the summer?
No. The lake turns over, and the oxygen levels are fairly consistent top to bottom. I guess there is a thermocline.
The lake turns over, that suggests that below the thermocline it might get lower oxygen in the summer?
Yeah, I was starting to say for part of the year there is a difference, but lake mixes well.
So it sounds like your bloom happens right after this turnover, right?
Well, it's a good suggestion to me. I would have to confirm that.
So what happens then is below the thermocline, the oxygen gets drawn down as this remineralization happens, both in the water column and in the sediments. And the oxygen gets used up, breaking down organic matter, and you end up with a good supply of P because it's anoxic, so it gets re-released from the phosphorus. And you also get a buildup of ammonium. And then when the turnover happens, you get this huge pulse of both P and ammonium out, and that feeds your cyanobloom in the fall. Sometimes people put in bubblers or oxygenators to try to prevent that thermocline from building up, and then you don't get the release of P in the same way, or you get a steady constant release of SRP and ammonium instead of that one big plug at the end.
Yeah, our lake is 10,000 acres. We're not going to do bubblers, but
yeah,
fascinating theory. Thank you for that.
All right, thank you, Rusty. We have another question from Sandra in the chat. She asks, but the release of phosphorus and nitrogen in the sediments does not happen unless there's oxygen depletion?
Oh, sorry, it does happen. It just happens slower and more steadily, right? And so more P stays bound up when it's oxygenated, but in the sediments, there's always going to be an anoxic zone. And so you can get, that happens naturally as you've got organic matter being broken down, this remineralization, use of oxygen in the sediment. You're always going to get to a point where there's no oxygen in the sediment. But as long as the surface of it is oxygenated, you're going to get some SRP and some ammonium coming out of the sediment, but again, it's a steady thing. It's when you get a thermocline in the lake and you can really build up large concentrations in the water that the turnover then can cause this huge pulse and release because it happens with a buildup in one event. Otherwise, it's happening slowly and steadily throughout the year.
Okay, thank you, Silvia. Are there any other questions for our speaker today? Okay. I'm not seeing any coming in. If anything comes to mind, feel free to reach out to me and I can relay questions over to Silvia. I'd like to thank Silvia so much for spending her time with us today. Very interesting talk, and thank you all for attending. I hope you'll come to our future seminar series. We have about one presentation a month lined up, and all very interesting topics. If you are interested in signing up to get emails from me directly when the seminars are coming up, please visit Ziegler's website, and there's a way to sign up for those emails there. So thank you, everybody, and have a great rest of the day.
Thank you all so much. I really appreciate you having me.